if you saw the email, then homework 3, which is the one where you're kind of manipulating those fermion operators and a little bit of the BCS theory, will be due on Monday, March 20th, right after spring break. And then homework number 4 will be due on Monday, March 27th, the following Monday. And so, homework 4. And so the basic concept, I think we have at least one person, if not more, here that is actually perhaps a math major. Some of you may have, if you're a math major, or maybe even if not, you might have said, or perhaps even in the context of your classical mechanics course, you might have heard of this form of calculus which is called a calculus of variations. And the idea is that we actually introduce a concept which is called the functional, and it turns out that a lot of things, like just an integral, for example, is actually a type of functional. And so in the context of the variational principle, the functional that we're talking about is actually the energy, in other words, or the expectation value of the energy. So the idea is that if I say the energy expectation value is equal to psi Hamiltonian operator psi, and and so that in a one-dimensional case, that would be integral dx of psi star of x. And remember that this would include both the p squared over 2m, which of course is minus h bar squared, plus the potential energy term, so that would be the Hamiltonian operator operating on psi, and then you're integrating with respect to x. Sometimes I put the dx at the beginning, or in quantum x, a lot of times we put it at the beginning. But the important thing is to note that, and in the case when we talk about in the problem that I'll be giving you, this is real, so this guy is really just equal to that guy. So kind of crudely speaking, this is actually so energy is actually a functional of the wave function, essentially, or of psi of x. In other words, it's a function of a function. That's the whole idea of a functional. That's why they sometimes call that a functional, because it depends on the value of psi for all x, or if it's a 3D case, all x, y, and z. And so the idea then is that in the calculus of variations, what we do, in the variational principle, in the variational method, what we do is we actually take a guess. We introduce some parameter, we take a guess as to what is psi, in other words, for given to, in this case, what would be the ground state? This is really most applicable if you're trying to figure out what's the ground state wave function of a particular system. So what you do is you'd actually take a guess. You just guess, okay, I think there's an extra spike in my potential over here, so I think my wave function should probably go down there. So you just take some guess, some reasonable guess, as to what form that has. And then what you do is you actually set the variation of this expectation value equal to 0. Now, in the calculus of variations, you would actually, it'd be like taking a functional derivative, like delta E, delta psi, and that's kind of an advanced concept. But in the context in which I will give you the problem, what we will do is we will simply have psi be the guess as to what psi is, be a function of a particular parameter. So then it becomes a max-min problem. So this is the context in which, why is that useful? Why is it useful to do something like that? It turns out that, of course, you got to be careful that you don't know a priori if you're minimizing or maximizing. You want to make sure you're in your guess. that whatever you do, you're actually getting the minimum, not the maximum. So it's like a max-min problem in regular calculus. But the idea here is that if I take a reasonable guess, such that this guy is minimized, there was a theorem that somebody came up with, I can't remember who, that the idea is that the ground state energy will always be less than or equal to whatever this expectation value is. In other words, that the variational principle is that the ground state energy can never be greater. If you take the variation, set that equal to 0, then plug your wave function to get psi, in other words, get the optimum value or optimum parameterized version of psi, plug that back in to get E, that will always be less than or equal to the actual ground state energy. And hopefully, if you made a good guess, it'll be very close to the actual ground state energy. And the reason, why did I get so gung-ho about this? Well, the reason is because I talked about the BCS theory last time, but it's a royal, and that's actually what they did when they did the full-blown BCS theory. I said, oh, they came up with some idea about the ground state, the BCS ground state, where you had a U and a V, and then of course you had these fermion operators, but then the question is, well, but how do you figure out what U and V are? Well, it turns out that what they actually did is they actually did a variational calculation in the original BCS theory. But that's kind of that would be like a really advanced, pretty complicated thing. I mean, you could actually read through it in Tinkam's book on Introduction to Superconductivity if you want to go through some of the details of what they did. But the idea is that, okay, they do something very similar to this. The only difference is that they also subtracted the chemical potential times the number of particles or something like this. You take the expectation value H minus mu times the number of particles in the fermion representation. That's the number operator that would go inside there. And you're minimizing that, and the chemical potential actually ends up just being the same as the Fermi energy. But and then going through all of that, they were able to figure out a lot of things. Figure out, okay, what's the ground state, what we call the BCS ground state, and then they actually went beyond that, actually trying to figure out what happens at finite temperatures and so forth. That would be a pain in the rear for this class to try to go through, okay, how do we do that for the BCS theory? So I thought instead of doing that, what I wanted to do, at least to introduce you to the concept of a variational or problem, variational principle, is I said, okay, let's go back to our old nice and simple tried and true particle in a box problem. And so what I do is I say, okay, let's start out with a box that looks just like what we've seen before. I think I go from 0 to A so it's uploaded right at the top of the list under content in Blackboard. And so if you look in there, then the idea is that, okay, I put in the next, I say, now this is our original box, but I don't want to make it that simple. We've already solved that problem. That's already a solved problem. I want to throw in something to make it slightly more complicated. And instead of using some of our old tricks that we did in the past, like trying the perturbation theory method, let's go ahead and we'll throw something in. It'll be a delta function right at, I think it was at 3a over 4, if I remember correctly, right here. So throw in a delta function right there in our potential. So this, so I think it was something like, what did I call it? I think I was called it V1a delta of x minus 3a over 4, if I remember correctly, for this delta function potential. And then I said, okay, now I took a guess on what I think might be a reasonable guesstimate for how the new wave function might look, or at least be a better estimate than just taking our original, obviously our original wave functions aren't going to work. It's got this extra thing in here. But suppose if this guy is here, then you might expect that should give you a little bit less weight. Ideally, you'd like the wave function to have a little bit less weight here, because that'll reduce the energy, essentially, is the idea. So get you closer to the ground state energy. So what I did is, okay, let's take a linear combination of the original ground state, which, if you remember, the original ground state looks something like this. And so that was the one. So the original psi1 was just root, in this case, because I use A, root 2 over A, sine of pi x over A, I think, the way I write it here. I hope I use the right terminology in there. And then, but because we want to try to push this down a bit over on this side as kind of a guesstimate for the next wave function, or for the next kind of to make it so that you reduce some weight. Notice if you have a sine function, the next one goes down, goes negative here. So that would create a dip right there if I added in a bit of the other piece right here. So so remember that one was root 2 over A sine of 2 pi x over A. And so now what I do is I say, okay, now as our trial wave function, let's try something like this, trial wave function. And this is literally a guess, it's just a guess. And so one could try to, other more complicated wave functions to see if the idea is that the lower, the further down you push your expectation value, the closer you are, I guess, to getting the actual ground state. Until you finally hit rock bottom, that you're as far down as you can get. That's it. That is the actual ground state. So this would be, so the trial wave function. I said, okay, let's try this. Let's try psi theta. I call it psi theta. This has this parameter theta. That's the one you want to figure out what value of theta is going to minimize the expectation value. So psi theta of x is equal to, and in order to guarantee that everything is already normalized, you could actually think of it like this. It's just a combination of cosine of this parameter theta times the original guy psi 1 of x plus sine of theta times psi 2 of x. And that kind of guarantees that everything's actually still normalized when you just write it, parameterize it in that way. And the way I wrote it, spelled it out in the homework, I actually spelled these functions out. I just wrote this out, the root 2 over A, and I had this guy, the sine of this guy here, and then I spelled that out, so that was root 2 over A times this guy right here. And so now what's going to happen? So what you're going to do in this problem is you're going to plug that into this guy, so we'll call this psi theta like this. And since it's real, you don't have to worry about that part there, so it'll be psi theta like that. I'll put the dx over here. And in this case, we go integrate from 0 to A, like that. Okay, now, just to kind of remind you, we can spell this out like this. So you're going to have, okay, I'm going to go ahead and go ahead and use the Dirac notation for a little while, just because that we can get rid of a few things right off the bat if we do that. So we have psi theta. We're going to have the, I guess I'll just write it like this, p squared over 2n term, that's the kinetic energy part of it, psi theta, plus, so this is the expectation, let me just rewrite this. So this is the energy expectation value we're trying to compute, plus, and this is where, okay, this is the part that gives you some, I'm being a little bit sloppy by writing it this way, but I'm just going to put it in there. That'll be the extra term, that extra potential, not the box part of it, but just this part of it right here, basically, that I want to put in. And so now now we can split out, so this is the part, let me first just split this part out. I'll call this term 1 right here. Let's call this guy term 2 right here. And so now let's take a look at term 1 right there. One is just going to be, well, you can see what's going to happen, okay? I'm just going to explain, and then I'll let you work through the algebra. Remember, this guy is cosine of each one of these is cosine of theta psi 1 plus sine of theta psi 2. Now, in principle, when you use the Dirac method, Okay. Remember that this whole thing really is just going to give you the energy eigenvalues, E1 and E2 operating. Remember, that's just going to give you pi squared. So in other words, this operating on this guy is just going to give you the energy eigenvalue, which is either going to be pi squared h bar squared over 2ma squared, or 4 pi squared h bar squared over 2ma squared, because that's the one for n equal 2. It's going to give you those two energy eigenvalues, and then what you're going to have is you're going to, in principle, you'd have 4 terms. You'd have a psi 1, psi 2, or psi 1, psi 1, psi 1, psi 2, psi 2, psi 1, and psi 2, psi 2. But remember that because these are energy eigenvalues, you can pull that energy eigenvalue outside here, and remember that these are orthonormal. So when you have the psi 1 coming up against the psi 2, that gives you 0, and vice versa. So the only terms that survive are the psi 1, psi 1, and the psi 2, psi 2, and then of course those are normalized, so those are just 1. So what is that whole thing going to reduce down to? So term 1 is that I want you to work through. Make sure you understand, okay, that this makes sense. Work through it. So term 1 is going to come down, is going to end up reducing down to nothing more than cosine of theta times the first energy eigenvalue, which is just